Hope y'all having a good morning so far. We're honestly about to just jump right into it. So, yesterday, went ahead and kind of started studying weights, biases, features, what they're doing, optimization algorithms. And as we were going down this path, there was just a lot of information that to me is going to be important that we're kind of not too sure on, right? So, we stumbled upon this video here in regards to
Day 11 of Fight
neural networks. Um, and today, as it is about an hour, we're just gonna go ahead and watch this, man, and take notes, relate it to what we're trying to do, and kind of push forward from there. So let's go ahead and pause that, and let's pick up back from the decision boundary. That's where we kind of started. We left off around weights, but let's start from the beginning. And yeah,
example, we've discovered a peculiar new fruit, which is purple and spiky.
so let's start from the introduction, actually. Uh, so far, what I've seen from this guy, I mean, the first 3 minutes or 4 minutes was amazing. So I have high hopes. Hopefully y'all can hear. Uh, that should be better.
Hello everyone. Today I'd like to try teaching my computer to recognize various doodles and images. Now, there are all sorts of techniques we could try using to tackle this problem, but the approach I'm interested in at the moment is neural networks. I first heard about these mysterious things about 10 years ago, and I soon set about trying to program one to get these little stick creatures walking around on their own. My code for handling the physics must have been a little buggy though, because this was the most successful result I ever managed to achieve. Although that's not counting the times where the creature fell over, and then somehow kept stretching its legs out further and further, which tricked my program into thinking it was doing extremely well. I eventually gave up on that and decided to try something a bit simpler. So here we have a little two-dimensional car with some sensors that detect the distance to the edge of the road, and these values get fed into a neural network, which then tells the car which way to steer.
I'm not sure if any of you are familiar with engineering or maybe common engineering projects, but on a robotics level, this is very common to have a essentially a path and getting through it programmatically, not using neural networks. So it's really cool being able to see this play out like this, and it kind of maybe in the future, uh, I might revisit this project because I had to do it in college, uh, and try it again using AI
Yeah.
neural networks.
Of course, it's completely hopeless at first, but if we let a bunch of them compete and then select the top few that drove the furthest to clone with some random mutations to their networks, and then let those compete and so on, we eventually get a car that's able to drive around happily on its own. The last thing I tried doing a couple of years ago now was training a network to identify handwritten digits. And once we've built our little neural network today, that's probably the first task we'll try testing it on. After that, we can see if the same code can be trained to recognize these tiny images of various.
Are we not familiar with this already? This looks like essentially convolution layers, and you get to a point to where it may have started with this one pixel, this pixel, this pixel, then it spreads out to two, and then eventually you outline the pattern, and through this pattern you can get the code.
Articles of clothing and fashion accessories instead. And finally, I'd like to try train it to recognize doodles of 10 different objects, such as helicopters, umbrellas, octopuses, and windmills.
What's really cool is, luckily, perhaps not luckily because we were searching specifically to help. No, because this is in machine learning in general. So, but luckily, and he happens to be essentially doing what we're doing as he sketches whether these are all pictures of receivers, cornerbacks, right? He is going to be using computer vision the same way that we are.
Actually,
Right? Computer vision is essentially what we're doing, if my understanding is correct. Yeah. Okay.
we could even try one last thing.
Since I read that a little fast. An AI field that teaches computers to interpret and understand the visual world from images and videos, enabling machines to see, identify objects, and classify them, and react, which is exactly what we're doing with receivers and cornerbacks. So,
Thing after that, which is attempting to identify these little color images, again of 10 different things, this time from cars to cats and birds to boats.
cars, cats, dogs, and cars.
This is obviously quite a leap up in complexity though, so if it proves too baffling for our simple network, then we'll have to return in the future to upgrade it to something like a convolutional neural network, which is
This word is everywhere. So, I'm curious, right? Because he spoke as if there's difference. Is the difference between neural network and a convolutional neural, right? He's speaking almost as if they're different, which, to my understanding, they're not. Mm, I see. I see. So this, I see. We have been learning the convolutional neural network. We have not. I see. And this, in my opinion, was leading a little bit to our confusion. Well, my confusion, because it was teaching us this with, and if you remember from the last video, I was going over how it's important to figure out the opposite, right? Figure out what would it be like without weights and biases? Why are we using weights and biases? What was the world like without it, right? What's a car like without braking? In order to understand the severity or the importance of braking. So we've been going over the convolutional neural network and how it uses the convolution layers, how it gets the spatial relationships, the local patterns, et cetera, et cetera. How it handles the I wonder if you want to say flattening is the way it's handling the height, width, and the RGB channels to where it goes 64 to 100 and 1212. I'm not sure. That's my current guess. So,
supposed to be much better at these kinds of problems. Anyway, to help figure out how we're going to build our neural network, let's imagine a simple example. We've discovered a peculiar new fruit, which is purple and spiky with orange spots and extremely delicious. Strangely though, some of them seem to be poisonous and will give you a terrible stomachache. So let's examine a few of these fictitious fruit, and we can see that their appearance varies in two main ways: the size of their spots and the length of their spikes. We could try drawing a graph with the size of the spots on one axis and the length of the spikes on the other. Then we could collect a bunch of fruit and plot them all on this graph based on those attributes. With some brave volunteer fruit eaters, we'd label which were safe and which turned out to be poisonous. Now, if the result ended up looking kind of random like this, then the spots and spikes probably don't have much relationship with whether the fruit is poisonous or not, and we'd have to think of something else. But if the data turned out looking more like this, then we're in business. We could draw a little line here called a decision boundary and say that any fruit we find that falls on this side of the boundary
so this is how we're and spoken on this again yesterday. This is how we're going to treat maybe one feature, right? Because we understand what a feature is now. The feature is the output of a feature from an input of a, let's say, pattern, right? It's more of a pattern. So, or a quality. I say quality in the sense of like a trait, maybe. Output of a trait. A trait outputted from an input is the best way, easiest way to explain it, right? Because we're saying the spikes are a feature. The way a person's body is leaning between receiver and cornerback is a feature, right? So here we can say this is body lean and this is foot position, right? So let's say this, as you go down this line of foot position, if your feet are staggered, you're more likely to be a receiver, right? So the more staggered you are, and then the more forward lean you have, the more likely you are to be a receiver. So it would be more like this, or I guess it would be more like forward lean, because this is standing straight up. And then you're leaning, you're leaning, you're leaning, you're leaning, you're leaning, you're leaning until you're really leaning here. And then this is like receiver lean, right? So anything above here is what a receiver would be leaning on. Now, that being said, you have foot stagger. So as it comes down here, your foot are slightly staggered, more staggered. So it's really going to come up like this, right? So it's going to be a, here's the decision boundary, and then these are going to be receivers because, well, really it'll be like started from here, right? Because you could have a lot of forward lean as a DB, but really it's the foot staggering where you'll eventually have to say, okay, this is too staggered for a DB. Or here you have the same concept. Okay, the spike is clearly too long at this point. Anything above this spike length is going to be dangerous. And then same thing over here. Anything above this spot length is going to be dangerous. So same concept. Once you find forward lean, anything above this forward lean is going to be a receiver. And then anything above this foot stagger is going to be a receiver. This gives you all receivers. These would be all cornerbacks.
Is probably
That's my guess. Again, I can't emphasize this enough. I am guessing. I am learning. This is 6 months later. Hold me to a higher standard, please. But as of right now, this is just
poisonous, and on the other side, it's more likely that it's safe. So, our very first step is to create a simple network capable of determining exactly that. We have two inputs in our problem, the size of the spots and the length of the spikes, and there are also two possible outcomes, safe or poisonous. The way we'll interpret these is if the first output has the highest value, then we're predicting that it's safe, but if the second output has the highest value, our prediction is that it's poisonous. Now, you might be thinking two outputs is quite extravagant. Why not just have one and say a positive value means safe and a negative value? Why not?
this to me sounds like it's using the softmax stuff here. Um, or the logics, right? If the output for confidence essentially of safe is higher than poisonous, then it's safe. If it's higher for poisonous than it is for safe, then it's poisonous, right?
Not just have one and say a positive value means safe and a negative value means poisonous. And we could definitely do that, but in future problems there'll be more than just two possible outcomes, so it's helpful to have a
So you think about this. Let's say I have, let's say I want to create an AI that handles the entirety of the defensive end, right? So you have your cornerbacks, but you also have your safeties, right? If you're not familiar with football, let's see here. Safeties, football, safety, good picture. So as you can see here, we have our receivers because they have that forward lean, they have the stance. You don't even need to know anything about football for any of this, right? Football, I mean, sorry, staggered feet, forward stance. Slightly staggered feet, more upright stance compared to the lean that's happening here. He's more straight up and down. He's more going forward at an angle, right? Then you have safeties back here who are the safeties to the cornerbacks, right? To the rest of the defense. They're the safeties. So let's say I'm working on the secondary, right? This is called the secondary right here. This would technically be your primary, right? But this is your secondary. And if I want to determine if it's a cornerback, if it's a safety, or if it's here, which is a linebacker, right? Because this is your line, this is your defensive line. So then you have people backing up your line. Then you have cornerbacks. Then you have safeties. So if I want to choose between, if I need to decide between a linebacker, a cornerback, or a safety, well, their feet are squared, their feet are slightly staggered, and they're pretty much standing straight up, right? So now I have three possibilities. How would I do that with one output, with one prediction number, right? I would have to somehow calculate, okay, if it's between negative infinity to uh, negative zero point 0.5, it's a safety. If it's from negative zero point 0.5 to 10,000, right? I would have to have arbitrary, uh, I would have to have arbitrary ranges of the prediction score in order to utilize it like that. Now, instead of that, as he was saying, it makes so much more sense to just have two outputs.
separate output for each of them. Alright, so these outputs obviously depend in some way on the inputs, but we don't know how much of an effect each input should have. So let's connect both inputs up to the first output, and these connections each represent a weight for essentially how important the inputs are to that particular output. So the actual value of this first output will be equal to the first input multiplied by the weight of its connection, plus the second input multiplied by the weight of its connection, and it'll be the same story for the second output. I've quickly
So, what's happening here, in my opinion, is we're saying we know weight gets adjusted by loss. So, if raising the weight here on a connection to output one is going to reduce loss, then the weight would be raised. And this output one, that doesn't sound right. I mean, the weight part's right. I'm not, I don't think output's doing what I think it is.
written
So
up
let's
some
keep
code
watching.
to perform this calculation, which you can see in the classify function over here. Then to visualize what's going on, there's this
weight values connecting each input to the first output. This is just doing the calculation that we already know, no bias. Um, and then it's returning.
Visualize function, which gets run for every pixel in the graph display, and it asks the network to predict whether a fruit at that point would be considered safe or poisonous, and then colors the graph accordingly. So let's see what this does. At the moment, it's very paranoid and seems to think everything is poisonous, but up in the corner here we have our network weights, so I'll play around with these a bit to see if I can get that decision boundary how we want it. Unfortunately, no matter what I do, I can only get the boundary to essentially rotate around the origin of the graph here, when what we need now is to be able to shift it vertically. So let's go back to the code and make a tiny upgrade to our network
Is that the
by
bias?
adding
Hey,
two new values called
let's
bias1 and
go.
bias2,
Let's
and
go.
these will simply be added onto our weighted inputs over here, allowing us to move those values up or down. Okay, let's give it another shot. So I'll fiddle with the weights again to try get the angle of the boundary correct, and then I'll move on to the biases. It's a bit finicky to control, but with some patient tweaking, we should eventually be able to hand train our little network to correctly classify the fruit in our training sample here. This was a pretty straightforward task though, so let's imagine that when we collected this fruit data, it actually ended up looking something like this instead. This is trickier, of course, because we can no longer separate safe from poisonous with a straight line, so we'll need to make some more upgrades to our network. One way we could try to improve the network is simply by making it bigger. It doesn't make sense to change the number of inputs or outputs because those are determined by the problem we're trying to solve, but instead we can create a new layer that sits in between. These in-between layers are known as hidden layers for whatever reason, and they can have as many nodes as we like, and we could even have multiple hidden layers, but let's keep things simple for now. So as our input values get fed forward to the next layer, they'll be multiplied by their weights, as we've seen before, and added up with a bias value, together creating a weighted input for that node. And once it's been
Oh,
computed for all the nodes in the middle layer, those values can then be fed forward in the same way to form the weighted inputs of the next layer.
oh.
Even for this extremely tiny network with only 12 weights and 5 biases, it would be quite tedious to write out all the calculations by hand like I did over here. So I'm going to throw all of this code out and start working on a more sensible solution. So I've begun by making
All
a
right.
layer script which stores
So let's look at this real quick. So it's of number of nodes in, number of nodes out. Your weights, you have your biases. Then you're creating a class um, that takes in the number, the nodes in, the nodes out, sets the constructor to that, and then creates a variable of double that take nodes in, nodes out. So then you're calculating the output and takes double or uses a double for the inputs. And you're saying the weighted inputs equals new double nodes out for int node equals 0. You loop through all the nodes. Uh, okay.
the weight values for all the incoming connections, along with bias values for each node in the layer. And these get set up over here based on the number of incoming and outgoing nodes. Just to clarify, in the code I'm thinking of this layer, for example, as having 3 incoming nodes and 2 outgoing nodes. Then this layer would have 2 incoming nodes and 3 outgoing nodes. And finally, this layer really just represents the values given to our network. It doesn't do anything, so it's not going to be an actual layer in the code. Alright, back to the layer script. All that's left to look at in here is this calculate output function, which takes in some input values and computes the weighted inputs simply by looping over each outgoing node, setting the corresponding weighted input to that node's bias value, and then looping over all the incoming values, multiplying each of those by the weight of their connection, and adding the result onto the current weighted input. For now at least, these weighted inputs are then returned as the output of the layer. Next, we have the actual neural network class, which contains an array of these layers. So when a network is created, it needs to be told how many nodes there should be in each layer, and it uses that information to set them all up, like so. Now, over here is the function for calculating the output of the entire network, and all this does is loop through all the layers, calculating the output of each layer, and using that as the input to the next layer. So once these inputs have been fed through the entire network, they've become the outputs. Finally, the classify function works essentially the same as before. It just calculates the output values and returns the index of whichever value is largest. So I'll create a network with 3 layers now, which will give us a lot more parameters to play with. And
As you see, he says it's returning whichever is largest, which is that prediction classification score, right?
let's see what new and exciting things we can do. Well, it turns out adding an extra layer doesn't help at all, at least not on its own. To make this boundary bend, we're going to need to allow the layers to have a non-linear effect on the output. So
Is exactly how he got here in the first place, right? We were we were confused about the nonlinearity effect of things. So what is that
let's go
exactly?
back to our design
And
and
activation
zoom in
functions.
on a
Look at
single
that.
node.
It all comes
In
together.
a loose analogy to biological neural networks, we can think of this node as a neuron and the weighted input over here as some sort of stimulus. If the stimulus is sufficiently stimulating, that should cause the neuron to fire, which in our model could mean outputting a value of 1, whereas
So what this means is the weighted input is with the weight and the bias all put together doesn't match anything for this node. If so, 1.
if the stimulus is small, the neuron wouldn't fire,
If no,
so
0.
we'd just be outputting 0. I'll refer to this output as the activation value, so we just need to write a little function that takes in the weighted input and computes that activation value, something like this. And let's quickly visualize that with a graph. So the x-axis here shows the weighted input, and the y-axis shows the corresponding activation value. Using an activation function like this should allow us to have more complex decision boundaries. Before we can try it out though, we'll need to quickly jump into the layer script, and instead of outputting the weighted inputs over here, let's pass them through the activation function and then output those activation values instead. So returning to the joyful process of randomly tweaking sliders until something happens, we can at last see that we're able to actually make simple shapes with the decision boundary. And of course, increasing the size of the network now would allow us to make increasingly fancy shapes. But this tiny network is already sufficient to correctly classify the made-up data we have at the moment.
That's insane.
By the
That
way,
is
you
insane.
might have noticed that the biases no longer simply shift the whole boundary up or down like they did before. Instead, they're just a way of easily shifting the value that goes into the activation function. So thinking of our biological analogy, it would be like a threshold that the stimulus needs to exceed in order for a particular neuron to fire. Now, one thing I don't like about our current setup is how abruptly and dramatically the output can change in response to just a tiny tweak to some of these sliders. So let's go back to our choice of activation function and maybe replace it with something like this instead, which simply smooths things out. This is called a sigmoid function, by the way, and it's just one of many different functions
Which is
that
also
people have
something we came
experimented with
across.
for neural networks. Here's a few others, just as a matter of interest. Anyway, let's go with this one for now and see how that affects things. So I'll mess around with these sliders once again, and we're now able to make nice smooth boundaries. And more importantly, making small changes to any of the sliders will no longer result in a drastic change to the output. Anyway, as fun as it is trying endlessly to train this network by hand, the goal of course is for the computer to do it all by itself. And for that to work, it's going to need a way to measure how well it's doing. One approach would be to simply count the number of known data points that are being classified correctly. But the trouble with that approach is that often making a small adjustment to one of the sliders won't actually change that number, meaning it's impossible for the computer to know if that adjustment was beneficial or not. So we should try find a more precise way of measuring progress. Let's think about the outputs of our network again, which are now being squished to somewhere between 0 and 1 by our sigmoid activation function. So if we give the network the inputs of a fruit that's safe to eat, we'd hope to see a 1 at the first output and a 0 at the second output, representing total confidence that it's safe.
Okay. So we were right about the outputs, depending on what it is after all the weights and biases. If it's matching safe, then you get your one. If it's not matching safe, or if it's not matching poisonous, then you get a zero for that. That's why you have
And
two outputs. If you had this one output, then you would be 0 and 1, yes, but then you would also need 0, 1, 2, maybe 0, 1, 3, 0, 1, 2, 3, the more and more that you add rather than just 1, 0, 0, 0, 0, 0.
for a poisonous fruit, that should be the other way around. So since we know what the outputs should be for our training data, I've added a little function to the layer script called the nodecast, which takes in the output activation value of a single node along with the value we want it to be. All it does is calculate the difference between the two and square the result, just to make it positive and I guess to emphasize large differences as being much more urgent to correct than small differences. Then in the neural network script, I've added a function simply called cost, which takes in a single data point, such as one of our fruit, and runs its inputs through the network to get the output values. Using those, it then adds up the individual costs of all of the nodes in the output layer to get an overall cost telling us how badly the network is doing for the given data point. We're most interested though in how the network is doing across all our data points. So here's another version of the cost function which takes in multiple data points this time and just adds up each of their costs and returns the average. So you can see that value at the bottom of the screen, and the goal of the network is now simply to find values for its 17 weights and biases here, which result in the smallest average cost. For the tiny network we have here, we could probably even get away with a brute force trial and error approach, but our networks are going to get a lot bigger as we tackle trickier problems, so we should definitely try to find a better solution. Let's simplify things by thinking first about this little example function, where, similar to the task of finding the weights and biases that minimize the cost function, we want the computer to find the input value that results in the smallest output, or at least some reasonable alternative. And of course, we'd like it to do this in as few steps as possible, not just calling the function millions of times until it finds a good answer. Now, our solution is going to rely on calculating the slope of the function, so let's try writing some code to visualize it. We can approximate the slope very easily by first defining some tiny value, which I'll just call h, and then calculating how the output of the function changes in response to this tiny positive nudge to the input. The steepness of the slope will
It's
just be
pretty
the
much a
change
normal
to the output divided
algebraic
by the
function.
change to the input that caused it. So as I said, this is just an approximation because we're technically calculating the slope between 2 points on the graph,
Okay,
but the smaller we make
so
h, the closer our...
this is going into gradient descent. I will say it's almost. Mm, let's keep watching.
approximation will be to what the true slope would be precisely at...
He's starting to kind of run past a lot of stuff, um, in a good way, right? I think it's my understanding that's lacking. Uh, so let's let's do this. Let's turn this over the weekend. All right, today's Friday, so what we're gonna do is chunk this into three sections. All right. So today we're gonna work on the first third, Saturday second third, Sunday the last third, and we're gonna fully go over this. So let's really understand the code. Why don't we do that?
each represent a weight for essentially how important the inputs are to that particular output.
I guess I should
So
definitely preface my programming isn't necessarily the best, right? I can do enough to do whatever I need to do at work. I can make simple programs, but as far as just the mathematical theoretical aspect of things,
the
it's
actual
more of a
value of
get
this
it done skill set I got. So
first output will be equal to
let's
the first input
let's
multiplied by the
let's walk
weight of
back a
its
little bit.
connection plus the second input multiplied by the weight of its connection.
Hmm.
And it'll be the same story for the second output.
Agreed. We understand this already. Okay.
I've quickly written up some code to perform.
Go. Double wait 1 1 wait 2 1 double wait 1 2 double wait. Okay, so this is wait values connecting each input to the first output. So the input is going to be the tensor. I want to say this is going to be the tensor. No, this is going to be the spikes and spots from my understanding. So spike spikes for object one, spikes for object two, and then this is spot for object one, spots for object two.
this calculation, which you can see in the classify.
So then you're running this class, or you're running this function, which classifies the given fruit as either safe or poisonous. So you get the input one, get the input two, double output one equals input one times weight 1 1 plus input two, right? Times weight 2 1. And then you have output two, which is equal to input one, the first fruit, times the weight of the first fruit to the second connection. And then input two times the weight of the second fruit to the second connection. All right. Return zero if output one is greater than output two. If so, return zero, return safe, I assume, or poisonous, one or the other. If output one, if the confidence and the poisonous aspect of things is greater than the confidence in it being safe. Otherwise, return one. Safe. Okay.
function over here. Then to visualize what's going on, there's this visualize function, which gets run.
So then you have run every pixel on the graph display to visualize the output of the network across a range of different input values. So you're saying double graph X, graph Y. This is the X and Y axes of the graph. Then you are running the classify function on the graph. Oh yeah, zero is safe, one is poisonous. So if safe is greater than poisonous, then you return zero. If predicted class equals zero, so the predicted class, I see. Predicted class is being, um, what's it called? Predicted class is saying when I measure the input one, input two, and that's the X and Y of the graph. Okay, so input one,
Run for every pixel in the graph.
every pixel in the graph display, right? So each pixel is going to be a fruit, right? And when you visualize it, you run your predicted class, and you're saying, okay, for this fruit, for a fruit, hold on,
Display, and it asks the network to predict whether a fruit at that point would be considered safe or poisonous, and then colors the graph accordingly. So
safe color,
let's see what
green,
this
red.
does. At the moment, it's
Okay, so we have these points. Has an x-axis and a y-axis attached to this point, right? So we're saying double output of one, whether it's safe or not, equals the input one,
the graph
double input one, which is graph x, which is the x-axis of this point, and then times the weight one, one. Each input to the first output. The first output is being safe, right? Plus input two, which is going to be the y-axis, right? Um,
accordingly. So let's see what this does.
which will be the y-axis here. And same concept, we're saying, okay, input two times weight two, the second output of fruit number one. So if this is greater than this, output 2, which is coming from input 1 and connecting to the second output. If safe is greater than poisonous, then return safe. Um,
At the moment, it's very paranoid and seems to think everything is
Huh.
poisonous, but up in the
I'll be
corner here
right
we
back,
have
actually.
our network.
Very sorry for the delay. Had something pop up. Where were we?
network weights. So I'll play around with these a bit to see if I can get that decision boundary how we want it.
Okay. So we're focusing on the decision boundary based off the weights. Now, what are we saying here exactly? These are the connectors to each output. So we have, we'll say, weight 1 1, weight 1 2, weight 2, or really weight 1 1, weight 1 2, weight 2 1, weight 2 2. So this is for your x axis. Let's say we're here, right? This is the weight, but no, because this is working in the decision boundary. I'm missing something.
Unfortunately, no matter what I do, I can only get the boundary to
I am missing
essentially
something.
rotate
Right?
around the origin of the graph here, when what we need now is to be able to shift it vertically. So
I'm missing something because the fruit is already classified. If it wasn't classified, it wouldn't have the colors already. So what is he doing that's allowing him to draw
So
the
let's go
decision
back to the
boundary?
code and make a tiny upgrade to our network by adding in two new values called bias1 and bias2. And these will simply be added on to our weighted inputs over here, allowing us to move those values up or down.
So let's do this. Let's do this real quick. Um, this code video, which allows someone to move a decision boundary around in a graph. Understanding. All right, we tried parsing it ourselves, breaking it down, but there's something missing here, in my opinion. But let's see. Because my understanding here is you're saying, hmm, I like this. I like it. I like it. Look at the code as C as math, not C sharp. All right. And maybe that's the issue, right? Maybe my understanding of the math behind things is a bit rusty. So that might be all right. So what this actually is, this is a 2D linear classifier. Input x, y equals input 1, input 2, right? So we're here. Output equals W11 x plus W21. I think that's weight 2, 1. I see. Weight 1, 1 x plus weight 2, 1 y plus b. This is a set of points where the classifier is undecided, switches from class 0 to 1, where output 1 equals output 2. What? All right. One thing at a time. So this is a 2D line classifier. What does that mean? Or linear classifier. Yes. Okay. Is a straight line to separate data points into two categories. The decision boundary, defined by a simple equation like W1x plus W2x plus b um, equals 0, where x and 1 are your features, W2 are weights, b is bias. So takes 2D points, x1, x2. Okay, 2D data points, x1 and x2. Let's let's understand this first, right? Let's deep dive into 2D linear classifiers. Um, let's
Hey, to understand linear classification, we're going to first plot some data. You can see two classes, the blue and the orange class. The task is now to choose a linear function which in 2D is simply a line to separate both classes.
see. Mm-hmm.
The problem is we have an infinite amount of possibilities to choose those lines.
Agree.
Here are three examples. The line closer to the blue class, the line closer to the orange class, and the line exactly in the middle.
Mm-hmm.
If we would choose the line closer to the orange class as separating function, then data points that are actually closer to the orange class might be classified as blue. The
Uh-huh.
same holds for the line closer to the blue class. Hence, the best line that we could choose would be the line maximizing the distance to both classes.
Agree.
This is the line exactly in the middle between both classes. As usually in math, we formulate a linear function as the following. F of x equals v times x plus b. V is the slope of the linear function and b is the bias.
This is literally y equals mx plus b. I'm not crazy, right? This is literally okay. I'm embarrassed it took me that long to put it together, but okay.
Our goal is now to find v and b describing a linear function. To do this, we can use two easy concepts from statistics, which is the mean value for the data points in the class and the covariance of a class. The mean is quite easy to understand. Basically, it is the average vector of all the data points in a class.
Uh,
For example, a class with two data points consisting of two features.
So the a data point, so D1, D0, D0, D1, D2, D3, D4, D5, these are what's being plotted. Yeah. Now, off of what's being plotted, they're gonna have your x and y values.
The first data point is the vector 1, 10, and the second data point is the vector 5, 0.
A five.
Now we add up both data points and divide by 2, which
Okay. Whoa.
is the number of data points in the class. The result is the average data point consisting of the vector 3, 5.
I see. So you're saying I take the x coordinates 6 divided by 2, you got 3, 10, 0 divided by 2, you have 5. Gotcha.
Since covariance is a little bit tricky to explain, I'm just gonna link the video about covariance in the description.
Thanks.
On a short note, the covariance matrix of a class tells us how correlated, on average, the features of an individual data point from that class are.
I don't think this is necessarily relevant. So let's come back here now.
As one node, we need now is boundary. Get that corner here. At the moment, it colors the graph.
Actually, no, 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 no. Here. So input x, y equals input 1, input 2. Two linear logics. Because you're saying input x and y is really is this the data point or is it the x and y coordinates, right? Yeah. I'm leaning towards the data points because then on output 1, you have the weight of 1, 1. Or you have input 1, weight of 1, 1 plus input 2, weight of 2, 1 plus bias. Let's try that again. Data features. Okay, so your inputs would be data features, height, weight, speed, lane, angle, pixel intensity, whatever. In the video you're watching, the author is visualizing the classifier by treating input 1 equals x coordinate, input 2 equals y coordinate. So, right, because he's saying here, the classified graph x and y, so this in itself is a data point. And inside of this data point, you have a double output 1, which is going to calculate based off the weight and the bias for output 1. I see weight 1, 1, input. So input 1 is your x-axis, working with weight 1, 1, which is for output 1. Then you have input 2, which is your y-axis, working with weight 2, 1, which is still, you know, working output 1, plus bias 1, which is meant for output 1. Then you have output 2, which supports the same exact x and y axis and does the same exact calculation because this is the determinant function, right? As long as I pass the same input, the result should be the same. That gives me output 2, which will calculate if it's poisonous. So based off the weight we're given, we'll determine if output 1 is poisonous or not, or is safe, and then output 2 is poisonous. So input of x and y coordinates equals input 1 and 2, two linear logits. Output 1 will calculate to a prediction. Output 2 will calculate to a prediction. If the output 1 prediction is greater than output 2, then the class is 0, which is safe. Else, class is 1, which means if output 2 is greater than output 1, then it's poisonous. And if they're equal to each other, well, shoot, better safe than sorry. Don't eat it. It's still going to be considered poisonous. That's it. Now, where does the decision boundary come from? The decision boundary is the set of points where the classifier is undecided. Switch from class 0 to class 1. Output, got you. Output 1 equals output 2. So plug in the definitions, rearrange. You see, you slide that over. Left side greater than 0, output 1. This essentially is, no, no, okay. Left side is greater than 0. 0, output 1 turns into out. Okay, so if the left side is greater than 0, output 1 is greater than output 2, which makes it safe. If the left side is less than 0, output 2 is greater than output 1, making it poisonous. So loop over every pixel, yep, and color that pixel, which is what we had. Given the classifier, write the exact equation of the decision boundary in terms of input 1, input 2, using the input variable names from the code. Input 1, feature 1, input 2, feature 2, feature value, dimension 1, dimension 2, color pixel, the graph is 2D feature space, each data point only works because of why he can move because changing the weights changes the lines, changes weights coefficients change, line rotates and shifts. He's not moving the pixels, he's cuts the space. So okay. So this is how we were understanding it. I'm still kind of not understanding though, right? So if we say that on the x-axis we're saying shoulder to angle, on the y-axis is distance from hips. How does that accumulate into a decision boundary? Right? So you're saying, well, these have to equal 0. So if you're saying the weight of 1, 1, yeah, hold on. Still not understanding how setting the equation to 0 creates a boundary within the entire graph. Hmm. Um, you're hung on how a single equation equals 0. draws a border across the whole graph, not just one point. Fix that. The classifier, right? So this is 0, 1, produces a number for every possible point. The classifier computes the weight of 1 minus weight of 1, 2 plus times x, right? So the x value plus weight of 2, 1 minus weight of 2, 2 times y, the y value, plus the sum of the biases, or the difference of the biases, whatever. This expression returns a number positive or negative. Each pixel on the graphs asks what number do I get if I plug in my x and y values. The boundary is all the x and y pairs where the number equals 0. The equation ax plus by plus c, which is what we're doing, ax plus by plus c equals 0. Is all points that satisfy it, not one point, an infinite set of points. I see. So the decision boundary are not data points that exist. Almost a hypothetical list of data points that, if existed, would equal to. Let's go. This is what you want to see right here. All right. Okay. And that's why by changing your weights, you're creating a new list of numbers that would equal 0. By adding to the bias, you're saying now we could slide up the graph because these new sets of numbers equal 0. Does that make sense?
Accordingly, fruited
So
for every pixel in
that's
the graph
that's it
display.
right there. That's it right
A
there.
bit multiplied by the
Okay,
weight for as inputs up.
let's take
We
another
don't know.
look at this.
Alright, so these outputs obviously depend in some way on the inputs, but
Uh-huh.
we don't know.
So the outputs depend. Let's and one of the best things I love to do is to be a little visual with it. Right? So let's visually follow along here. Let's just do this. Is that enough space? Need more space. Okay. To change the size. Okay. So what we got here is we're saying the output relies on the inputs, right? Which makes sense.
How much of an effect each input should have.
But we don't know how much of an effect each input should have. Because technically you could say, okay, the input comes in and we're going to divide the input by 99, and now the input doesn't have much an effect of an output. But if we say we take the input and multiply it by 100, now the input has a huge factor on the output.
So let's connect both inputs up to the first output, and these connections each represent a weight for essentially how important the inputs are to that particular output.
So how important? I see. Oh my God. Oh my God. So input one, we can treat as the forward lane of a player. And then input two, we can treat as their specific foot positioning and the distance between their feet, right? This is a person, yada. But we're calculating the distance between their feet. Now, the forward lane, to me, is more important than the separation of the feet. Why? Because come here, defense, football, full, picture. See if we can find something secondary. Okay. So as we can see here, like a new tab, we look at something like this, right? And you say, really, I I actually, now that I say that, I think it's gonna be this way. So we're gonna say the foot positioning, right? The gap from toe to back heel, well, the gap from toe, well, to toe from toe, well, from front heel to toe, from front heel to toe. You see from front heel to toe, from front heel to toe, or sorry, from front heel to toe, from front heel to toe. The difference between this is the most important thing. So the weight is going to be larger in regards to the distance from from front heel to toe. And then you'll have your forward lean, which has an importance, but you can see he's just about as upright as he is. Whereas he is a bit more bent over if compared to him. Whereas, et cetera, et cetera, et cetera, right? So our weights are going to be higher here and lower here because that will lead to more loss or less loss when determining between the two.
So the actual value of this first output will
Oh,
be equal to the
I'm not gonna lie. I am working right before work. I got 8 minutes to get online, so this was wonderful. We're gonna stop here and let's actually go ahead and write some notes real quick. So, weights produce effect to each input, right? Forward lane less than foot distance by altering the weights, create a new decision boundary. Bias allows for more flexibility within the decision boundaries. And yeah, I mean that this is an we 100% now came
first
to the
input
conclusion that we
multiplied by
needed,
the
and I very much see how that's meant to work. So that's great. Um, to think we spent pretty much an hour for the first 5 minutes. It's tough, but everything from here is kind of going to fall into place. So let's keep going through, man. Each day we'll keep chugging through this, and by the end of this, and we go back to our project, I have a sneaking suspicion that everything's gonna be a lot easier. So let's keep it up. All right. So tomorrow we did 10, and we're saying creative work. All right. Wonderful. Well, I hope y'all learned something with me, and I hope that y'all have